artificial intelligence is running out of room on Earth. The power grids are maxing out. The cooling systems are draining freshwater supplies. And the land required for new facilities is becoming impossible to find in populated areas. This video explains one serious engineering proposal to solve all three problems at once by moving the hardware off the planet entirely. One hyperscale data center, the kind that runs large AI models, consumes the electricity of 100,000 homes. U.S. demand for AI computing is projected to jump from 4 gigawatts today to 123 gigawatts by 2035. That is a 30-fold increase in roughly 10 years. At the same time, these facilities use millions of gallons of fresh water every day just to keep servers cool. Power grids in Virginia, Texas, and Ireland are already turning away new data center construction because there is simply no capacity left. Space solves three ground problems simultaneously. First, energy. The sun outputs more power than all of Earth's electricity production combined. And in orbit, none of it is blocked by atmosphere or clouds. Second, space. There are no zoning laws, no land costs, and no neighbors to push back against industrial facilities. Third, environmental impact. Moving compute infrastructure off Earth removes the power draw, the water use, and the heat pollution from the planet entirely. The engineering challenges are real, but the physics of the solution is sound. The key orbit for maximum solar power is sun-synchronous orbit. A satellite in this path maintains a constant angle to the sun throughout the year. No nights, no seasonal variation, no atmospheric interference. Solar panels in this orbit are 5 to 8 times more productive per square meter than identical panels on Earth's surface. The result is a 100% duty cycle. Power available continuously around the clock with zero carbon emissions and zero fuel cost once the hardware is in place. Space does not cool electronics. It traps their heat. Vacuum is an insulator. Without air molecules to carry heat away, a server in orbit behaves like a thermos. Heat builds up inside with nowhere to go. Fans are useless without air. This is the real thermal challenge. Not cold, but the inability to shed heat. The engineering solution is large flat radiator panels mounted on the outside of the satellite. These panels conduct heat away from the processors and radiate it as infrared light directly into deep space. No water, no fans, no electricity required. On Earth, the atmosphere and magnetic field absorb the vast majority of cosmic radiation. In orbit, hardware is exposed to a continuous stream of high-energy particles with no protection. When a charged particle strikes a transistor, it can flip a stored bit, changing a 0 to a 1 or vice versa. This is called a single-event upset, and it can cause software crashes, corrupted data, or in AI systems, incorrect outputs. The fix requires 3 layers: physical shielding to block low-energy particles, radiation-hardened chip designs that resist electrical disruption, and error-correcting software that detects and reverses bit flips in real time. Every kilogram launched to orbit costs money, and traditional data centers weigh thousands of tons. At current launch prices of roughly $3,000 per kilogram, moving even a modest server rack is economically impractical. The game changer is fully reusable rockets. SpaceX's Starship is designed to carry 100,000 kilograms to low Earth orbit and land back for reuse, driving costs toward an industry target of under $200 per kilogram by 2035. At that price point, the mass tax drops low enough for commercial orbital compute to become viable at scale. Traditional radio links cannot move data fast enough for AI workloads. A standard satellite radio link delivers 100 megabits to 1 gigabit per second. A modern data center internal network runs at 100 gigabits per second, 100 times faster. The solution is free space optical communication, laser links between satellites and to ground stations. These systems shoot focused beams of infrared light directly between spacecraft with no medium required. Demonstrated speeds reach 10 terabits per second, matching terrestrial fiber. Starlink is already deploying inter-satellite laser links across its constellation as proof that the technology works at scale. A direct comparison makes the trade-offs clear. On Earth, power comes from a maxed-out grid that is costly and carbon-heavy. In space, power is free 24/7 solar with zero carbon. On Earth, cooling requires millions of gallons of water and banks of fans running continuously. In space, cooling uses zero water, only passive radiator panels facing deep space. On Earth, maintenance is straightforward. Technicians walk the floor and swap parts hourly. In space, maintenance is extremely difficult. There is no quick fix for a failed component. Hardware must be designed from the start to tolerate failure and operate in degraded states. For organizations are leading the push toward orbital compute. Google's Project Suncatcher is testing AI chips, specifically tensor processing units, in space by 2027, targeting a scalable orbital infrastructure system. SpaceX is providing the heavy lift launch capability and has sought FCC approval for up to 1 million satellite data center nodes. NVIDIA is supplying the foundational Hopper and Blackwell AI chip architectures, both designed to survive the radiation and thermal environment of low Earth orbit. StarCloud is the agile startup moving fastest, achieving orbital computing milestones ahead of the larger players. In late 2025, StarCloud launched a 700-watt NVIDIA H100 GPU into orbit. That single payload represented a milestone. The first time a commercial, power-hungry AI chip designed for large-scale machine learning was operated in the vacuum and radiation environment of low Earth orbit. The team used it to train NanoGPT, a small but real large language model, entirely in space. No ground-based compute assisted. The experiment proved that unmodified commercial AI hardware can survive orbital conditions long enough to perform meaningful work. It changed the conversation from theoretical to demonstrated. The trajectory over the next 10 years points toward orbital compute becoming a real infrastructure layer. Swarms of interconnected AI satellites will form distributed processing networks, effectively orbital supercomputers with no single point of failure. Some industry analysts project that the majority of new compute capacity built after 2035 will be in space rather than on the ground, driven purely by the economics of free power and free cooling against rising terrestrial energy costs. The long-term impact is a fundamental expansion of human technological infrastructure beyond the atmosphere, a shift as significant as the move from mainframes to the cloud. The case for orbital data centers is not science fiction. It is an engineering problem with known solutions and real hardware already in orbit. The power crisis on Earth is measurable and worsening. The physics of space cooling and solar power are well understood. The launch cost curve is moving in the right direction. The remaining question is not whether orbital compute will happen. It is how fast the economics will make it inevitable. If this video was useful, subscribe to LumScience. Leave a comment. Do you think AI will be running from orbit within your lifetime?